7 seats are positioned in a row at a movie theater. Rebecca, Wayne, Heather, Garrett, Mark, Ashley, and Alice want to sit together in this row. How many different ways can they be arranged? If there's 7 people and 7 seats, that means the first seat there's 7 people who could potentially sit down. Now let's say that Rebecca happened to sit here. There's 6 people still left standing. Well, that leaves 6 options for this seat. And let's say that Wayne happens to sit here. Well, then there's 5 people standing, so there's 5 options for this seat. And it continues all the way till you hit the last seat, and there's only 1 person standing, so there's only 1 option. When you start at a number and multiply by 1 integer smaller till you hit the number 1, this is called a factorial. This here would be 7 factorial. When you multiply it out, it gives back 5040. So there are 5,040 ways that these 7 people could arrange themselves. The formal definition of factorial is x factorial, and it means start at integer x and multiply by 1 number smaller until you hit the number 1. Some special cases that we should discuss: 0 factorial is always 1, and 1 factorial is 1. Let's try evaluating some other factorials. 4 factorial means start at 4 and multiply till you hit the number 1. 4 times 3 is 12, and 12 times 2 is 24. So 4 factorial is 24. If there are other things to be worked out, such as a parenthesis ahead of the factorial, you want to subtract first. 8 minus 3 is 5 factorial. This does not equal 8 factorial minus 3 factorial. Factorials are not distributive. 5 factorial says start at 5 and multiply till you hit 1. But hopefully you notice that 4321 is the same thing. So what we could have really said is that 5 factorial is 5 times a 4 factorial. And so we could have worked this out as 5 times the 24 that we knew 4 factorial was. And this is 120. To access the factorial symbol, type in the number you wish to look at. Then hit Math, scroll over to Probability, scroll down to number 4, and hit Enter for factorial. Then hit Enter again. The Poisson distribution is used to calculate the probability of a rare event. Of course, you want to assume that the average is a small rate. The average will indicate by mu. You also assume that the observations are made over many small intervals of time. And x would be the number of events that occur within that interval. If these conditions are satisfied, then we can say that x has a Poisson distribution with parameter mu. Most Poisson distributions are skewed right, and the center is at mu, and the spread, or the variance, is given by mu, and the standard deviation would be given by the square root of the variance, or the square root of mu. The formula to work out probabilities for Poisson distributions, the probability that random variable x equals a number x, is mu to the x, e to the minus mu, divided by x factorial, where x is an integer somewhere between 0 and n, and where x factorial means start at that value and multiply by 1 number smaller till you hit 1. This factorial is the same thing we just went over at the beginning of the lecture. Putting together the shapes and spreads, just to give you an idea, Poisson distributions usually have a shape something like this with a center at mu. In 1898, Vaughan wondered what the chance was of a Prussian cavalryman being killed by a horse kick. 10 Army Corps were observed for 20 years. We will focus on the observations made over 1 year for 1 corps. The total number of deaths due to horse kicks amounted to 122. So if we want to know the average number of deaths due to horse kicks over 1 year period, we'll say that that number is 122. And the symbol to represent the average is mu. What is the probability of 0 deaths due to horse kicks in 1 year? We're looking for the probability that x equals 0. And we know from the previous page that the probability x equals a number is mu to the x, e to the minus mu, over x factorial. So this should equal mu, or 122, raised to the x value of 0, e to the minus mu, divided by the x value of 0 factorial. Anything to the 0 power is 1, and 0 factorial is 1. So this simplifies to e to the negative 122. And when you type this in your calculator, it'll give back 1.04 e negative 53. Just in case you're not familiar with this notation, this is scientific notation on your calculator. It really means 1.04 times 10 to the negative 53rd power. It means 1.04 with the decimal moved a total of 53 decimal places. What I'm saying is that there's a string of 52 zeros here, and then the 104. This is practically 0. So this tells us the probability that no one will die from a horse kick in 1 year is almost 0. It's highly likely someone's going to die by being kicked by a horse. To type this into the calculator, you're going to type in 122 raised to the 0 power times e raised to the negative 122nd power. Make sure you hit this key for negative. This key means minus. Divided by 0 factorial. To access your factorial, hit math. You can hit the over arrow 3 times or just hit this arrow 1 time and come down to factorial, hit enter, and then enter again. Here's an example of how this could be used today. The number of births in a hospital occur randomly an average rate of 1.8 births per hour. Let x equal the number of births in a given hour. There's 2 things we need to note. First, we need to note that this is a Poisson distribution and that the average mu is 1.8. Second, we need to know that this average applies specifically to a 1-hour interval. It says per hour. This distribution would change if the interval changes. For part A, what is the probability of observing 4 births in a given hour at the hospital? This is the probability that x equals 4. Let's go ahead and get that probability formula. The probability that random variable x equals a number little x is mu to the x, e to mu divided by x factorial. Plugging in our values, we know that mu is 1.8 raised to the x value of 4, e to the minus mu, divided by x factorial. In this case, nothing simplifies, so we'll type this straight into our calculator, and this is 0.0723. In part B, what is the probability of observing 2 or more births in a given hour at the hospital? And notice it says a hour. Same thing in part A, it said a hour, and that matches our interval up here, per hour, for 1 hour. So these are all working out just fine. Now this is going to be a little challenging to calculate because if you're thinking of births at a hospital, you know that no one can give birth, maybe 1 person, 2 people, 3 people, but where's the upper limit? How do you know when the number of mothers who needs to give birth will end? What I'm asking is, what's the maximum? Because if you have to go from 2 to a maximum, what is that number? And that's the idea with the Poisson distribution. There's some maximum. You know naturally there's going to be a stopping point, but you don't know where that stopping point is. So instead of trying to find the probability of these values going up to some unknown stopping point, we're going to use the concept that all of these values should sum to 1. So if we do 1 minus 0 minus 1, if we subtract out the pink dots, that should leave over the black dots, the probability of being greater than or equal to 2. So we're going to rework this as 1 minus the probability that x is less than or equal to 1. Or another way you could have written it is 1 minus the probability that x equals 0 minus the probability that x equals 1. This is 1 minus the probability that x equals 0. That's the average of 1.8 raised to the 0 power, e to the negative average, divided by the x factorial, minus the probability that x equals 1. that's the average 1.8, raised to the x, e to the negative average, divided by the x factorial. Another thing we could have done that may help you see this better, down here in the general formula, everywhere that there's a mu, you could have replaced it with the actual value of the mu. Remember, x is Poisson with parameter mu, so you could have just plugged in the 1.8, and then hopefully that lets you see that all we did next was change the x values. For the first one, the 0, we changed the x's to 0, and for the 1, we changed the x's to a 1 in the formula. But everything else stayed constant. There's some simplifications that we can make happen. Anything to the 0 power is 1. 0 factorial is 1. 1 factorial is 1. And an exponent of 1 really is not needed. So in the end, we could have rewritten this as 1 minus e to the negative 1.8 minus 1.8 e to the negative 1.8. And when you type this in your calculator, you'll get back 0.537. What is the probability of observing 5 births in a given 2-hour interval? I've written what we said on the last page again. We said x was Poisson with parameter mu equal 1.8 for a 1-hour interval. But in this question, I'm asking for the probability that x equals 5, but this time over a 2-hour interval. Here's the start of an interval and the end of an interval. And over this one interval, you're going to have 1.8 births. And now this is the start of another interval and the end of another one. And over this interval, again, you'll have 1.8 births. And this keeps repeating up to however many intervals you want. There's always 1.8 births within that interval. And let's just call this particular interval interval t. If I'm looking for a 2-hour interval, what I'm basically saying is that I want to take two successive intervals back to back and find the average there. And that would be 2 times 1.8. It would be 1.8 plus 1.8. You're adding the averages for the intervals. So this gives back 3.6. So now, instead of saying that it's a Poisson distribution 1.8 for 1 hour, we can say that x is Poisson 3.6 for 2 hours. And now the 2 hours and 2 hours match. We can proceed with the problem. So we're now ready to answer the question, what is the probability of observing 5 births? We can use that same probability formula. The probability that random variable x equals a number is mu to the x, e to the minus mu, over x factorial. Here, our new average is 3.6. We want to raise this to the 5th power, e to the negative average, divided by x factorial. In this case, nothing simplifies, so we'll need to go straight to the calculator. And this gives back 0.1377. Let's talk about transformations with the Poisson distribution. Let's say that random variable x is distributed as a Poisson distribution, and let's say that its average is lambda here. We'll use a different symbol. And let's also say that lambda is the average number of occurrences in one interval. Visually, we could represent one interval like this and say that within this interval, lambda will happen on average. And then here's a second interval with another lambda, and here's a third interval with another lambda, all the way to wherever you end up stopping. Let's just say at your teeth interval you decided to stop. Well, if I said change it from the average number of occurrences in one interval to the average number of occurrences in t intervals, what you would do is find a new average, and this new average would be mu equal lambda times t. You could think of it as the average number of occurrences in t intervals. So now you can say that x has a Poisson distribution with parameter mu, where mu equals lambda times t, and then work out your probabilities from here. These problems are going to require you to distinguish between individual probabilities and cumulative probabilities. Individual probabilities are just the probability that x equals a number, something like the probability that x equals 5. And what you're going to do is look for words like exactly or only. The second type, a cumulative probability, will be looking at intervals of values. And I want to walk you through how to work these out for different cases. Let's say you start with the probability that x is less than but not equal to some value n. So if you're less than it but not equal to it, you're actually starting at n minus 1 and then finding probability smaller than that. So when you work this out, you need to work it out as the probability that x is less than or equal to n minus 1, because you never actually equal. It's an open circle on the n. You don't start there, you start at the n minus 1. Or, if you wanted to flip it around, you could say it's 1 minus the probability that x is greater than or equal to the n value. Remember, this entire thing sums to 1, so if you take 1 and subtract out the n plus 1, and all the values above this, it will leave over the values you were looking for. Here's the next case, the probability that x is greater than n. If you're greater than n, you do not equal it, you equal the value 1 bigger, and then all values above that. So you could work this out as the probability that x is greater than or equal to n plus 1. If you wanted to flip this around and use complement rule, you could say it's 1 minus the probability that x is less than or equal to n. Remember, the entire number line sums to 1, and if you take 1 and subtract out the n minus 1, and all values smaller than this, it leaves over the values you were looking for. Here is your last case, the probability of being bound between two numbers. And let's just say that this is for the case when m is less than n, as I've drawn on the number line below. If you're bound between but not equaling the m and the n, what you actually equal are the m plus 1, the n minus 1, and all values in between here. So to work this probability out, what you could do is say it's the probability of being at the n minus 1 and smaller, minus the probability of being at the m and smaller, and when you subtract these values out, so you subtract this one out, subtract this one out, keep subtracting them all out, it leaves over the inclusive values that you were looking for. In winter, before turning the bulls out to pasture with the cows, the bulls need to be sperm tested. The veterinarian checks the sperm for concentration and mobility, and then assigns a score ranging from an F to an A+. Bulls with scores between C and A+ can be turned to pasture with the large cow herds. Scores of C- can be used for small cow herds. Scores below C- are not to be used. A lurking variable that will affect the rate at which a bull will breed is libido. For instance, Angus bulls are known not to have a lot of libido, whereas Charolais are known for their high libido. Let us say that a Charolais turned to pasture with a large herd of cows breeds an average of 3 cows in 4 hours. Let's go ahead and note that to ourselves. It says average of 3 cows, and we know that our interval is 4 hours. And we also know that this is going to be a Poisson distribution with mu equal 3, and we could say that random variable x is the number of cows bred in 4 hours. Here's our first question. What is the probability that the bull breeds exactly 6 cows in 4 hours? We're looking for the probability that x equals 6. Here's the probability formula for the Poisson distribution. We're dealing with a case where mu is fixed to the number 3, so let's go ahead and replace mu by the value 3. Now that we have a general formula, let's go ahead and work through the case when x equals 6. This would be 3 to the 6th power, e to the negative 3 over 6 factorial. Typing this in our calculator, we get back 0.05. So there's a 5% chance that the bull would breed 6 cows in a 4-hour time period. Thinking about this on a number line, the bull could breed 0, 1, 2, 3, 4, up to as many cows as it really wants to breed or is capable of breeding in a 4-hour interval. If we want the probability of being greater than 2, that means we are not including 2, but we are including 3, 4, 5, or however many more he's capable of breeding. Since there's no known upper bound, we cannot work the problem out by finding the probability of being greater than a particular number. What we'll have to do instead is say that the entire sample space sums to 1. And now out of this sample space, we're going to subtract out a portion of it. If we subtract out the 2, the 1, and the 0, that should leave over the values that we were looking for. So we'll subtract out the probability that x is less than or equal to 2. Another way you could have written this is 1 minus the probability that x was equal to 0, minus the probability that it equaled 1, minus the probability that x equals 2. Plugging this in the formula, we'll first plug in 0 in the x positions. Now we'll plug in the 1 and then we'll plug in the 2. We could go through and clean this up a little bit. 3 to the 0 power is 1 and 0 factorial is 1. 1 factorial is 1. An exponent of 1 isn't really needed. 3 squared is 9. 2 factorial is 2 times 1, or 2. So with all these cleanups, this can become 1 minus e to the negative 3, minus 3e to the negative 3, minus 9 halves e to the negative 3. When you type this in your calculator, you'll get back about 0.577. What is the probability that the bull breeds 10 cows in 8 hours? And 8 doesn't match our interval of 4. So from here to here, here's a 4-hour interval, and the average was 3 in this 4-hour interval. Here's a second 4-hour interval, and again the average was 3. So in a 4 plus 4, in an 8-hour interval, the average should be 3 plus 3, the average should be 6. So what we can say is that we now have a Poisson distribution with an average of 6 for 8 hours. Working this out, this is our new average, mu, 6 raised to the x power of 10, e to the negative mu, all divided by x factorial. And that gives back 0.041. What is the probability that the bull breeds 1 cow, but this time in a 2-hour interval? So let's think about our interval. Here's 4 hours, and in that 4 hours, the cow can breed 3. So if we chop the 4 hours in half, if we divide by 2 to get a 2-hour interval, we should chop the 3 in half to get an average. So we can now say our new average is 3 over 2, or 1.5. This is now a Poisson distribution with an average of 1.5. This is mu 1.5 to the x power, e to the negative mu, divided by x factorial. This gives back 0.335.